Okay, so let's solve that for v, right? That's going to be the hardest thing, right? I think we can rewrite this way. Can we? And then we can square both sides, right? So 1 minus v squared over c squared. Yeah. And then we can do I call this the Murray switch. Isn't that true? 1 minus a equals b, then 1 minus b equals a. It's like a crazy thing. And then I think we can multiply by c, can't we? And then to get v, we're going to square root, right? So we get c times the square root of... Isn't that a beautiful thing? Not in the data packet, but there it is. Isn't that easy to remember? That's pretty easy to remember. That looks a lot like the original formula, doesn't it? Yeah? I mean, this whole thing is pretty hard to solve. If you sat there, I used to just give this to people, and they'd sit there and poke the calculators for a long time and just get sort of random answers. No, not that one either. You know? But that's the answer, is that it's the speed of light times this, right? This, by the way, if you want to give the answer in terms of a factor of the speed of light, like 0.85c, this is what it is that thing in parentheses there, right? Okay? So if we want to get this answer, we just go square root of 1 minus 1.8 squared over 1.2 squared. How did I know it was 0.8 over 1.2 without even saying like proper time and blah, blah, blah? Yeah, and then here's the other clue. If you go and do it the other way, you get a negative under the radical, and then it's imaginary, right? So it's always the solution for this thing. This is the solution specific to time, right? But the general solution is that the velocity is c times the square root of 1 minus, and then it's always small squared divided by big squared, right? Because you can't do the other way. Your calculator will go, yeah? Okay. And then go ahead and give it like that. That's fine as meters per second. But this is going to be, if you just do this thing under the radical, right? And this is sort of a radical idea. Thank you. Joke acknowledged. I like that. 1 minus 0.8 squared divided by 1.2 squared. Don't you get 0.745 c? Right, or how many sig figs do we have? Oh, we've got a lot. We got 3 sig figs, so it's 0.745. Yeah? So I rounded too much on the bottom there, yeah? Yeah. And of those two answers, the one in terms of the speed of light would be the more common one to give. That's right. Yeah. Yeah, sig figs on the bottom there aren't quite right. Yeah, that's right. So this is when it says the solution for velocity on your little note guide. Put that guy in there, right? It's always going to be when length contracts, the contracted length will be on top and the non-contracted length will be on the bottom. When mass dilates, the bigger mass, the moving mass will be on the bottom and the small mass will be on the top. When time dilates, right, the dilated time, the time that took longer, will be there, and the non-dilated will be the proper time will be up there, right? So you don't have to really worry. If you just keep these guys in mind, right? If you just keep those guys in mind and then do this, right, you're set. Show. Yeah. Yeah, this would actually be v equals c divided by the Lorentz factor, because the Lorentz factor is like this reciprocal thing, right? But it's not really the Lorentz factor, because the Lorentz factor has the velocity and the speed of light there, right? Here it's just small divided squared divided by big squared. Notice that this one is small and big, small velocity, big velocity, right? So it's the same notion. Okay, so now this one is a weird one. Everybody has a hard time with this one, right? They have identical watches. Joe is moving with respect to Mo at 0.85 c. Let's suppose he's going in a big circle, so we can just sit there and watch, right? Somehow he's withstanding the g-force of going in that circle at that speed, right? Let's not worry about that, right? And we're just sitting there watching him go around, around and around he goes, right? Okay? And so if Mo is sitting still and Joe is moving, right? 15 seconds elapse on Mo's clock. How much time elapses on Joe's clock? If it's ticking slower, is it more time than 15 seconds elapsed on his clock, or less time? Less time. So rather than sit there and struggle with which is proper time and which is not proper time, okay, let's just make that time less. Use this factor to make 15 seconds less. IQ on the line. Now, if you don't know whether to multiply or divide by that factor, do both. Pick the answer that gives you less time. Do we all understand why it's less time? Yes. The clock is ticking slower. So when you're talking about elapsed time, it turns everything on its head. It takes longer to tick, therefore less time elapses on the clock. Yeah. The moving clock ticks slower, yes? Okay, so if these are the same clocks and they normally would stay in sync, the moving one is going to lag behind, therefore show less at any time elapsed time. That's right. I'm going to kick myself on the IB test.